In this video, we're going to look at stress and strain in a beam. Let's say, for example, that we had a cantilevered beam as shown here, and we applied some force out on the end of the beam. And we wanted to know how the beam reacted to this force. That is, we wanted to know perhaps how much it deflected. We wanted to know what kind of stresses and what kind of strains were occurring at any particular point in the beam. Or we wanted to know what was the reaction at the wall because of this force. Now to do this, we're going to use something called thin beam theory. And thin beam theory basically assumes that both the length of the beam, which we'll call L, and the width of the beam, which we'll call B, are much greater than the thickness of the beam, which we will call H. So L is much greater than H, and B is much greater than H. Now to solve the problem, we have to know two things. First of all, we have to know when we apply this force, what kinds of forces and moments show up in the rest of the beam. And then secondly, we have to know how do these forces and moments cause various strains in the beam. So first thing we do is we start with a two-dimensional stylized version of this particular beam. And we'll draw it like this. And we'll say we'll apply some force F at some distance L from the wall. And we want to know, let's say, what's going on here. That is, we want to know what are the forces and the moments that must be created in order to react against this force being applied at the end of the beam. So to do that, we cut our beam at position X, and we take what's left over, and we draw a free body diagram. Because the beam is statically loaded, that is, it's not moving, accelerating, or anything like that, we know that the sum of the forces have to be the same. Because we're applying only one external force, F, the other forces have to arise at the cut of the beam. That is, there's a plane where we cut the beam, where the internal forces in the beam are reacting against the external applied force, F. Now there's also a moment created in the beam, because we have to be able to resist the tendency for this beam to turn if we just applied these forces. And I've drawn the moment using a convention that we use, which is that on a leftward facing face, we draw the moment in the what would normally be considered the negative direction. I'm not going to go into big details about the sign convention. We're mostly just interested in magnitudes of things in this particular video. But as the problem gets more complicated, you need to make sure that you figure out what the sign convention needs to be in order to make sure that you get the correct answer. Now it turns out for thin beams that the internal force created at the plane where we cut the beam is negligible. That is, the force isn't negligible, but the effect of the force is negligible compared to the effect of the moment at the cut beam. So if that's the case, we can solve for, all we need to do is solve for the moment at this cut face, and we can write that by knowing that for static equilibrium, the sum of the moments has to be 0, and that's equal to minus m, as we've drawn it here, minus F, the applied force, times the moment arm that force is acting on, which is L minus X. If you remember your right-hand rule, when we're looking at a coordinate system with the standard X and Y, a moment in the counterclockwise direction will have a positive value. And in this case, the moment at the internal face we've drawn as a negative value because of our sign convention, and the force is acting downward, and so therefore we have a negative moment from that as well. When we solve for the moment m, then we get m is equal to minus f times L minus x. So that means, for example, at x equals 0, that is, at the wall, the moment is equal to minus f times L minus x, but x is just 0 at that point, and so we get the moment is equal to minus fl. At x equals L, where we're actually applying the moment, we get the moment at L, sorry, let me put a 0 there, is equal to 0, because L minus x is equal to 0, and that makes sense because there's no moment at the point through which the force happens to be acting. Now, once we know the moment in the beam, now we can calculate the stresses and strains that are created internally to the beam, or on the surface of the beam as well. To do that, we look at a thin section of the beam, which I will draw like this, and we apply a moment to it. So our beam is of thickness h. We'll set our coordinate system such that y equals 0 goes through the middle of the beam. That is, at the top it's equal to y equals h over 2, and at the bottom it's equal to it's y equals minus h over 2. And we'll apply a moment of strength m to one face, and in order to maintain equilibrium, we'll apply a moment of strength minus m to the other face. When we do this, we expect that the top